So today we're going to do functions. All right. So let me just start with the unofficial definition. So a function f from x to y is a way of producing an element of y, an element of big Y from an element of big X here. Okay, so X and Y are sets. The official definition is as follows. Well, okay, let's start with an example though. Let's do an example. Okay, so we could do something like f goes from the real numbers to the real numbers, and f of x is given by x squared plus 1. All right. So another notation. So there's sometimes another notation that we introduce will be, sometimes we write like this, x squared plus 1. Okay, so you're taking something in the domain and you're mapping it to something in the codomain. So we're going to call this side over here, this is the domain. This will be the codomain of the function. All right. Okay, so the official definition and so this kind of unofficial definition was used by Euler, okay, and is really old. Okay, so this is like in the 1700s. The people were using functions for a long time. They used sets. I mean, actually, they didn't use sets for a very long time, but they used geometry to talk about functions. But the official definition of a function, as I'm going to present it now, did not come until the late 1800s, okay, with Dedekind and Cantor and these people. All right. So a function is a triple x, y, and gamma of f, where x and y are sets, and gamma of f. So sometimes this is referred to as the graph of the function. The graph. Okay, so this is what's called the graph of the function. Sorry, it's a subset of here. So we have the data is 3 sets. This set's in here such that for all x and x, there exists a unique, so this is not a not symbol. So there exists a unique y and y such that xy is a pair inside the graph. Okay, so this is kind of the unintuitive. This is the intuitive idea. This is the unintuitive idea, but the official definition. Okay, so let me give some remarks on the terminology. Okay, so for x in x, so we define f of x to be the unique element of y such that x, y, x comma f of x is in the graph here. Okay? So this is considered as the primitive thing, although we think of f as being the rule, right? This is the basic object. Do you have a question?
Yeah, is that saying that there does not exist a y?
No, so this doesn't have to do with not. This symbol here means that there exists a unique. A unique. Okay? So in particular, this means that if xy1 is in xy1 is in gamma f and xy2 is in gamma f, this implies that y1 is equal to y2. All right? So if you have these two things, then these two things are equal, and that's what it means to be unique. Okay? That's the uniqueness statement. Okay? So we define this thing to be in this way. So so here, okay, so I need to say that. So in the triple, x, y, gamma of f here, x is called the domain of f. Okay, y, so this is the domain. Y is called the codomain of f. This is the codomain. And sometimes this is called the source as well. Same thing, this is called the target. Okay, so we can also specify what the images are. But before I talk about images in range, so image will mean the same thing as a range, I want to do some examples to talk about these things, okay? So these are, and so now, so x and y can be arbitrary sets. And so when I specify an example, right, I'll be just pulling pairs out from random, okay? So there's no way of getting the function. I'm giving you the function, and then we'll once I give you the function, then we'll talk about properties of the function, okay? So let's do an example. So, okay, let's first do this one here, okay? So this function here, okay, so I could have as well made another function where the codomain was smaller. So notice here that every number here is going to be bigger than or equal to 1, okay? So, okay, so let me make a last little remark here. So two functions are going to be equal if and only if their triples are going to be equal. Okay? So in our example, so another example. So consider g from the real numbers to 1 here. This is this interval here, given by the same rule. Given by g of x is equal to x squared plus 1. Okay? So I just am declaring that to be the domain here. So this function for this class is distinct from f in the previous example since the codomains are different. Okay, so here, I'll just use some words and then I'll define the words later. But here, this function is what's called onto. Everything in the codomain is hit. Okay, this function here is not onto, because say -100 is never hit. Okay, so these functions are considered different because of the way that I specified the codomain. And so in order to specify a function fully, we need to specify the domain, the range, and the codomain rather than just a rule. Okay, and the rule is also encoded by the graph. right? So, so using this technical definition, we could have two rules which give the same graph, and then we consider those functions exactly the same. All right? So let me make this other technical point. So, so this is the first technical point, right? Right? Is that you need to specify the range in the domain, so that you need to specify a range, or sorry, not a range, a domain and codomain, to fully specify, to fully give the function. Okay, and function. So one more thing, let me just do the graph for this thing. So what is the graph for this particular guy here? Just so we can see a graph first. So here, so example of a graph of gamma g. Okay, so so this is the graph of y is equal to x squared plus 1. So this is the gamma. This is gamma of f. This is from the first example. And it's also equal to gamma of g from the second example. So some textbooks, I should give you a little warning, some textbooks, rather than requiring the quality of these triples, right, they just say that two functions are equal if their graphs are equal. And they just identify functions with their graphs. Okay? In this class, since the book follows the convention that you need the domain and codomain to be the same, then in order to for the functions to be equal, we'll be doing the same thing. Okay? Does that make sense? So these graphs are the same. So and the graph looks like this thing. So these are the ordered pairs, you know, in the product. So notice that this thing here, R cross R. Okay? It's also, gamma g is a subset of R cross here, 1 to infinity. But this thing is a subset of here. And actually, these two things are equal. All right? So since this is a subset of this, we can write that subset there. All right. So, OK, so let's do some more examples. OK? Let me give you. Oh, OK. Actually, I was going to talk about the second technical point before I do that. So let me talk about the second technical point. So the second technical point is that the way that the way / rule you use to define functions does not distinguish them. Okay? And so I'm going to give two functions that have seemingly different rules, but have identical domains, codomains, and graphs, and hence will be equal. All right? So here's the example. Okay, so consider the functions f, and we'll do f from z to the real numbers, and g from z to the real numbers. So these are now two different functions given by two things. Right? So f of n will be -1 to the n, and g of n will be equal to cosine of pi n. All right? So we have two functions like so. So note, so let me draw the graphs. So the graphs. So let's do this. OK. So so here I will label the integers here. So this is 1, 2, 3, 4. This is 0, -1, -2, -3. And let's do the graph here of the second one. OK, so we'll do 0, 1, 2, 3. So 0, 1, 2, 3, -1, -2, -3. And so here let's do the graph of f, and let's do the graph of g. All right? So what is f of 0? OK? So it is 1 here. OK? So what is f of 1? So f of 1 is, sorry, -1. So it goes like this. All right. So it alternates like this, so on and so forth. So this line, this is the line y is equal to 1. This is the line y is equal to -1. This is the line y is equal. I'll do the same thing over here. OK, now let's look at this rule. Okay? So this rule is the exact same thing. So here, right? So OK, so now my claim is that, so since the domain, codomain, so since the domain of f, the codomain of f and the graph of f is equal to the domain of g, the codomain of g, and the graph of g, meaning that each one of these things are equal, right? The functions are equal. So f is the same thing as g. Okay? And it doesn't matter that we specify how we wrote down the rule. Okay? We only care what the output is, right? So we only care that what the graph looks like. Does that make sense? Okay. So so let's say, but if we considered another function, h from, let's say, the integers to say -1 to 1, it'd be considered, we would consider it different as a distinct Okay, so this one we consider as distinct since here the codomain is different, right? Okay, and so this thing actually has the exact same graph as well, right? So does that make sense, guys? Okay. Yeah.
Never mind.
Okay. I mean, so there is a way. So if you want to distinguish these things, you can consider these things as objects other than functions, right? And you could specify, you could make some definition as to like rules, right? And then, but that's not what we're talking about. We're talking about just as functions, they're the same. Okay? So if you wanted to come up with some mathematical way to distinguish these objects, you could. But then you'd have to specify more data other than just the function. Okay. Okay, so now I want to talk about some vocabulary of functions, okay? So some vocabulary that goes with functions. So like I said before, I think I introduced the word onto, right, or surjective. This function's surjective here, and this one with this domain here is, or codomain is not surjective, okay? But we'll talk about that a little bit more. So let me do some more vocabulary, okay? So is that me? Okay. I was like, okay. So let's do another example. So here I'm just going to make up a random example, okay? So So this is a random example with finite sets. Okay, and so what I'm going to do is I'm going to draw a function. Okay, so I'm going to take, let's say, 4 points here. And let's do 5 points here. Well, let's see. Do I want to do 4? Let's do 5 points here and 4 points here. Okay. So and let's call this set. This will be the set X, and this will be the set Y. And let's call these A, B, C, D, and E. And we'll call these 1, 2, 3, 4. Okay. So, and then I'm going to specify the function so that this guy maps to this guy maps to this guy maps to this guy, and then you repeat. So this guy goes up here, and this guy goes up here. Okay? So, so let's specify a function out of this cartoon. So here, so I just chose this randomly. Okay? So, so we can make a function. A function out of this cartoon. Okay? And here, so here, X will be the set A, B, C, D, E. Y will be the set 1, 2, 3, 4. Right? And then the graph. Okay, so the graph specifies which ordered pairs we hit. Okay, so here we'll have A1, B goes to 2, C goes to 3, and D goes to 1, and E goes to 2. Okay, so we just kind of, so this is what we were, this is the graph here. So the data, x, y, gamma of f, specify a function. Okay, so these things specify a function, and we can write, you know, f of A is 1, f of B is 2, f of C is 3, f of D is 1, and f of E is 2. So we use the same notation like we did before. Okay? So now we've kind of we've made this the three things that consist of function, that make the data of a function, and we specified how to make this rule. Okay, and so now we can talk about we can use words. So this is here. This is what's called the image. Okay, so sometimes. So let me give some terminology now. So terminology. Okay. So there's several things that we can do for images. We can talk about the image of a point or the image of a set. So if f of x is equal to y, we say y is the image of f under x. Okay? So e.g. 1 is the image of A under F. All right? So that's what an image is. But we can also talk about images of sets. Right? So the image of A subset of X is, well, this is f of A. So it's defined to be f of A. And it's the set of y and y such that there exists an A and A where f of A is equal to y. Okay? So for example, in our particular example, what would the image of, let's say, AB be? If, yeah, exactly. A, B, then f of A is the set 1, 2. Okay? So this is the things that all the things that get hit here. All right, so we have images of functions, and we have images of sets, and then there's the image of the function itself. Right? So we have the image of, so this is the image of A. So the image of X here is the set of Y and Y such that there exists an X and X such that f of X is equal to Y. So this is, the notation for this is Im of f, or this is called, sometimes we call this f of big X. Okay? Okay, and so for our example, what's the image? The image of f is the whole thing, right? So this is 1, 2, 3 here. So notice that it's not the codomain, right? So this is the set 1, 2, 3, right? So note that this is distinct. This is a subset of the Y, which is the codomain of f. And in this example, so the codomain of f is not equal to the image of f. All right, so this is, okay, so let me do this. Let me do it like this, okay? So this is the image. Okay, does that make sense about what the image of f is? All right, it's a subset. So this is the image of x under f. Okay, so let me keep this up, and I'm gonna modify this a little bit. So in addition to talking about images, we may talk about preimages. Okay, so preimages. So the preimage of a set B, a subset of Y, is this set, F inverse of B. So it's the set of Y and Y, or sorry, X and X, such that f of X is an element of B. Okay? So let's look at an example. So B is equal to, let's say, the point 1, 2. Okay? So here, f inverse of B. So what would this be? What is the preimage of these points here? So it's just the things that they get hit by. Okay? So this is the preimage. So it's all the things that hit those guys. All right? So this would be the set A, B, D, E. Okay? So this is the preimage. Okay? And now the preimage of a point let's say B and Y, is the preimage of the singleton set. Okay, so F inverse of B, so this is defined to be equal to F inverse of this set here. So there's kind of abuse of notation is that you can plug in sets and points into this thing, okay, into this F inverse thing. So let's do an example of this one. So F inverse, So let's do an example. F inverse of, let's do the point 1, right? So this is just the points A, D here. Okay? And so what is F inverse of 4? It's the empty set, because nothing is hit. Right? So we have these things in this example. Does that make sense? All right. Okay, so we have preimages, images, preimages. Okay. So I need to introduce some more terminology. All right? So, so let me draw some doodles again. So I'm gonna draw some random doodles. Okay, so this is going to be on injectivity, surjectivity, and more examples. Okay, so it's hard to tell which one to give first, but what would you guys want to see a picture first or the official definition first? Picture first. Okay. So what is injective? Okay, so here's an injective example. So let me draw a doodle. Okay. Okay, here's an injective. Okay, here's y and here's x. Okay, so this is kind of a doodle of an injective map. Okay, so here's a surjective example. So here, let's do I don't know, you could have something like this. Okay, so here's x, here's y, and then this is the function f. Okay, so do you guys see what's going on here? So this one is not injective, right? And this one is so here. So now I'll give you the definition. Let me give you the definition. So the official definition. Okay, so the definitions. So a function f from x to y is injective, or sometimes this is called one-to-one, right? If, okay, so this is read one-to-one, to-one. So surjective and injective come from French words. So injective and surjective. Okay? So if for all x, y, and x, f of x is equal to f of y implies x is equal to y. So that's when a function is injective. So a function f from x to y is surjective if and only if. So all definitions are if and only if. So I could have written if there, but it really means an if and only if, right? We talked about that before. So a function is surjective if and only if for all y and y, there exists an x and x such that f of x is equal to y. So this is saying that every point gets hit. And this is saying that no two points hit the same thing. So this is saying everything in the target is hit.
Is surjective the same thing as onto?
Yeah, onto, or onto. Yeah. everything in the target is hit. And so this is saying no two things, no two distinct elements map to the same thing. Okay? One more definition. F from x to y is bijective if it is both one-to-one and onto. Okay, so this is saying that well, that's what it says. Okay, so for finite sets, they have to have the same number of elements. All right. One-to-one and onto.
Yeah.
I mean, we say one-to-one and onto often instead of just saying bijective. I don't know. I mean, I can't think of one off the top of my head, but there are other words. Yeah. So you have to be aware that there's other words for these things. I can't think of one off the top. I always use the word bijective. So, I mean, sometimes you use the word isomorphic as sets. So bijective is equal to isomorphic as sets. So this is also saying that this is a monomorphism of sets, and this is sometimes called, so this is also, let me give another word. This is a monomorphism of sets. And this is a monomorphism, so this is another way to say this, and this is an epimorphism. Of sets. That's another way to say, that's another terminology. Okay, so I'll just do a circle to make them look the same. Yeah? Yeah?
Switching everything to something because
No.
sometimes just one x is equal to one y. Just maybe.
No, but this is a special function. Not every function is injective or surjective. So we raise it to, so everything is hit. So for example, in this thing, every guy here has a preimage. They may have two preimages, but they at least have one.
Yeah, but must be something. There must be something for example, x is equal to 4 and y is equal to 3. There is only f for is equal to times 3 and x is equal to the fourth one.
Fourth one. Here. Yeah.
And y is equal to the third.
Yeah.
Yeah.
This a third one. Yeah.
So there is only one x is equal to one y.
Yeah.
So they are not hit.
It's hit. This thing is still hit.
Oh.
So for every y, there exists an x.
Oh, I missed it.
So it says for every y, there exists an x. That's what it's saying. Yeah.
So the previous example,
Mhm.
the one where we were talking about A, B, C, D, E to 1, 2, 3, 4, and 4 wasn't hit. Would
Yeah.
that be an example of something that's neither?
Yeah. So this is an example. So the first example, so the example here, so this example where I did 1, so A, B, C, D, E, 1, 2, 3, 4, 4 like this, where I did this thing, and then I went up like this. So this is neither surjective nor injective. Okay, so this one is neither surjective nor injective. No, we just call it a function. So, you know, it's not special, right? It's not. It has no special properties. It's just, you know, doesn't. It's not surjective and it's not injective. Okay, so let me give you some more examples, huh? More examples. Some more examples. Okay, so here's an injective example. So we'll do j, I'll call it j goes from r to r squared, and we'll define j of t to be equal to tt. So this is a map here, which takes t on the real number line, right? So this is r, this is the domain of j, and it maps it to, well, it maps it to an element here, j of t, which is tt. Okay? So the idea of in math, there's kind of a principle that injectivity and surjectivity are kind of at odds with each other sometimes. Okay? So this one here, this map here, j, right? So this is R2. This is the codomain of j. So this thing here is this thing here is injective. So this is an injective map. So j is injective. So note that if j of t1 is equal to j of t2, so this implies that t1, t2 is equal to, or t1, t1 is equal to t2, t2. So that's the definition, right? So that's the definition. So this implies that t1 is equal to t1, t2. Okay? So this is an injective example. Let me give you a surjective example. Another surjective example. So a surjective example. Okay, we'll define this map P. I'm using the letter P because sometimes this is called a projection. Right? So, and it takes x, y, and we'll just map it to x here. Okay, so here, here's the picture. So we'll take, so this is R, right? This is another copy of R, I guess. So this is R2. This whole thing is R2. And so what it does is it takes the point x, y here, and it maps it via P to this point x. Okay, so this is this projection map. So this thing is surjective. So notice that for every x in, so I guess let's say it like this. Let's say for every s in y, so this is just a single copy of y, you can choose, can pick, you know, any s and then t, right, in R2 to get p of st is equal to s. Okay, so this means that it's surjective, right? All right, so let's do a bijective example. All right, so let's consider, so let's do bijective example. Okay, so consider R from R2 to R2. So this is given by R of xy being minus yx. All right, so this is what this thing is. And so what this does is it takes it takes points over here Excuse me. So you guys aren't supposed to know this yet, but I'm telling you. So this one, excuse me. And this one will rotate. This one rotates everything. So this point here gets mapped to something over here. So this is supposed to be 90 degrees from the original one.
Would it be the other way because it's negative on the x?
So the new x coordinate is negative. Yeah, so you have to get away from the fact that y is attached to this thing. Yeah, so r does this. It rotates. It's a 90-degree rotation. So this is r is a 90-degree. Okay, intuitively, we can unrotate, right? So since you can unrotate, right, it makes it, so that's one way of telling if something's bijective, is that if you can undo it, then it's bijective. Okay? By the way, let me just tell you something fun about complex numbers. So, you know, you have xy here. This corresponds to x plus iy. So if I multiply this times x plus iy, so I squared is -1, so I is like this. So I is the square root of -1. So this is how you write, this is a complex number here. And this is a R2. OK, so this establishes a bijection between R2 and the complex numbers. OK, so this makes a bijection between these two things. And I times this, so if this is a map here, I times this number. So this is ix plus I squared y. And so this is equal to -y plus ix. So the map R from here to here corresponds to the bijection, to multiplication by I in the complex numbers. So this is not really so relevant. I mean, it talks about a bijection here, but that's totally irrelevant. I just wanted to let you guys know how you can think about rotations really quickly. Multiplication by complex numbers is as a function is a rotation and a stretching of space of the plane. Okay, so which is kind of a cool thing. So this is why there's another reason why complex numbers are useful. So you guys should take a complex analysis class, and they talk about that stuff. Anyway, okay. So we have these. So let's talk about, say, like, let's talk about images and preimages here. Okay? So in the first example, in the injective example, so in the injective example, so let me write it down again. So j of t is equal to tt, and j was a map from r to r squared. So the image of j, so this is the set of tt, right, in R2. So this is the domain, or this is the codomain for t in a real number. So this is the line that I drew here. So this is the line y is equal to x. So this is not the graph of the function, right? This is the image. So this is this line here. That whole line is the image. Okay, does that make sense? That's the image. Okay. So notice that this thing's injective. It's not onto. So preimages of points here, right? So if I take a point here and I look at its preimage, it's the entire vertical line. Okay. So the entire vertical line will be the preimage there. Okay. So we talked about domains, codomains. Let me see if I missed anything else. Okay, so let me give you another bijection. So here's another bijection. So another bijection.
Just let you know, I believe class.
Oh, class are we up right now? Okay. Oh, okay. Yeah. So we'll continue with more examples next time. All right. Thanks.